Most AI agent architectures fail in production because engineers misunderstand the math behind token pricing. A model that looks cheap on a pricing page will still bankrupt a project if you ignore how multi-step workflows actually consume tokens. I'm the bearded AI guy, your digital avatar here to translate the latest deep dive architectural analysis from the human architect. Today, we are looking at 3 models released in March 2026, Mistral Small 4, GPT-5.4 Mini, and Nemotron-3 Super. These were not positioned as standard chat models. They landed with a specific purpose: to serve as fast, tool-capable agent backbones meant to run multi-step workflows of scale. The immediate reaction from engineering teams is to see the sub-$1 per million tokens marketing and assume their production API, or application programming interface, bills will drop proportionally. An API is simply the software bridge that allows your application to send text to the model and receive a response. But evaluating these agent models using single-turn leaderboard scores hides the true cost of multi-step production runs. A model that answers a single trivia question perfectly might completely break down when forced to loop through 5 different tool calls. To understand why, we have to look at a structural property called context explosion. Context explosion refers to the rapid, uncontrollable growth of the text history that a model must read during every step of an agentic workflow. This animation illustrates the core problem. In multi-agent systems, token growth is multiplicative, not linear. Every time the agent takes a step, the entire conversation history, along with lengthy system tool traces and intermediate plans, gets re-injected into the prompt for the next turn. NVIDIA tracked this exact phenomenon and found that multi-agent workflows can generate up to 15 times more tokens than standard chat workloads. Therefore, a mathematically cheap model that fails a tool call and requires 5 automated retries is vastly more expensive than a higher-priced model that gets the correct tool call on step 1. Proving a model works in production requires a realistic multi-step evaluation harness. Standard coding benchmarks completely miss the looping nature of agent tasks. This flowchart outlines the human architect's 5-step minimal agent loop required for realistic testing. The loop begins here at the intent parsing phase, moving directly into structured tool planning, where the model selects the correct schema for the job. Next is the execution phase, where the system actually runs the requested tools and parses the resulting text outputs back into the model's context. This is the critical node, error handling and the retry loop. If the model formats a request incorrectly, the system catches the error, forces a repair plan, and loops right back to execution. Once a model gets stuck inside this looping scaffold, the metric of tokens per task completely dominates tokens per second. If a model lacks strict schema compliance at the planning stage, the resulting infinite retry loops will erase any advertised cost savings. Tool calling is uniquely fragile when you combine it with long context memory. Performance degrades sharply under 3 specific stressors: massive catalogs of available tools, complex multi-turn dependencies, and bloated JSON responses. JSON, or JavaScript Object Notation, is a standard text format used to store and transport structured data between servers and web applications. Here is the painful reality for engineers. A tool calling failure is often an integration and parsing defect in the serving stack, like vLLM, rather than a failure of the model's actual reasoning capabilities. To programmatically catch these integration defects, you have to isolate the model from the tooling. This snippet shows a custom evaluation harness, specifically the step executor class, highlighting how it explicitly decouples the model backend from the tools. By looking closely at the step metrics class, we see the exact operational metrics required to prove a model is working: the schema valid and tool calls valid Boolean fields. Tool reliability is partly a platform feature. Your chosen model is only as capable as your serving stack's ability to parse its structured outputs. Now let's evaluate how the 3 March 2026 models actually survive this harsh multi-step reality. We start with GPT-5.4 Mini. It features a massive 400K context window and delivers phenomenal structured outputs, supported by a deep, highly integrated ecosystem. However, its pricing reality is strict. It costs 75 cents per million input tokens, but it is not sub $1 on output, sitting at $4.50 per million. Depending on your ratio of inputs to outputs, its true blended price pushes much higher. Next is Mistral Small 4. This model offers true deploy-anywhere token economics at just 15 cents per million input tokens and 60 cents per million output, alongside a 256K context window. The critical catch with Mistral is implementation. Using it requires explicit prompting for JSON mode, and developers must navigate known technical debt regarding reasoning parsing within standard open serving stacks. GPT-5.4 Mini wins on strict schema enforcement and platform reliability, but you pay a premium for that stability. Mistral Small 4 wins on raw token economics, provided your engineering team can manage the serving stack's sharp edges. Finally, we have Nemotron-3 Super. This is a 120 billion parameter model utilizing a sparse MOE architecture. MOE, or mixture of experts, is a technique where only a small subset of the model's neural networks activate for any given prompt, saving compute. It runs on a hybrid Mamba transformer backbone and was trained on a massive 1 million token context. Its primary advantage is massive throughput, hitting top-end generation speeds near 475 tokens per second on optimized infrastructure. Look at this comparison. That raw speed is an intentional architectural choice, designed specifically to offset the latency thinking tax. While a slower model drags, Nemotron instantly processes the massive text blocks caused by context explosion. The strict caveat for Nemotron is deployment. Its tool calling and JSON mode support is highly fractured and varies wildly depending on which API provider you choose to route through. Nemotron-3 Super is the ultimate high-speed, open-weight bet for multi-agent loops, but only if your chosen API provider actually exposes its specific tool calling features. This brings us back to the core operational decision: how to accurately budget for these multi-agent systems. The headline price per million tokens is merely marketing. The true engineering metric is the blended per-task cost, calculated after accounting for the model's error and retry rates. There is also a hidden danger in format compliance. A model that generates perfectly valid JSON, but populates it with the wrong arguments, will silently break your downstream logic without triggering an immediate catchable error. Because of this, long context reliability must be explicitly tested inside of active tool calling loops. Testing a model's memory on plain text document retrieval is not enough. The primary architectural trade-off becomes clear. You are either paying a token premium for a highly compliant, fully managed model, or you are self-hosting a cheaper model and spending your resources building rigorous parsing guardrails yourself. In agent architectures, you either pay the API provider for reliability, or you pay your engineering team to build the integration glue. The final verdict? For raw throughput and long context headroom, deploy Nemotron-3 Super. For absolute format compliance and error recovery without maintaining custom Docker images, choose GPT-5.4 Mini. For open weight, deploy anywhere economics, where you handle your own parsing, target Mistral Small 4. If this architectural breakdown helped clarify your production stack, subscribe to the Bearded AI Guy and share this video with your engineering team. Drop a comment below with what nuances we missed, or tell us what specific AI architectures you want the human architect to analyze next. Always remember this fundamental rule of multi-step AI systems. Your production agent is only ever as cheap as its weakest tool parser.